Okay, so before we start with lecture notes, I just want to run over a couple of things. Make sure that you are getting access to the Achieve homework, that if you're taking lab, that you have already started your assignments because they're due tonight. And that's about it. I think that's the most important. And that our first exam starts Thursday. Is that what it says in the syllabus? I have it running for 24 hours. Typically, we do the exams where you would have a specific amount of time, like an hour and a half to take it. But we found that with summertime, it's a little different because you're taking other classes. It's hard to come up with a time. So we're just going to open it for a window. As long as you take it within that window, you're good. So that being said, we're probably going to come close to finishing chapter 12 today. Who's excited? Nobody?
It seems more scary than me.
Do what?
Finishing like a whole chapter in like one day, maybe even 30 minutes.
It's really not bad. It really isn't. Finishing a chapter in one day, I will tell you, I love teaching 112. I love teaching it in fall, spring, but I really love teaching it in Maymester because I can teach without a break in the content, right? So in the regular semester, if I teach Tuesday, Thursday, I gotta wait all the way till Tuesday to finish what I was talking about on Thursday, and then people forget, they don't look at it, they don't review, so I have to kind of remind. It takes more time. With it this way, I like it much better. So we can just move right through. All right. For those of you online, I will keep checking the chat and try to respond as often as I can. You will hear me cough. I don't have COVID. I have COPD, emphysema. Look it up. Cough like this for 15 years. And when COVID hit, I felt like I needed to wear a t-shirt that said, not COVID, been doing this. And so it begins. Jacob, what does that mean? So, Chem 112. Does everybody remember everything from Chem 111? Not everything, but the important things, right? So we're going to jump right in. We're going to talk about solution. And we're more specifically going to talk about ways to describe a solution in terms of concentration. So there are some things that we need to know. And one of the things we need to know is when we talk about a solution, we have a solute and we have a solvent, and those together make up the solution. That's going to be very important as we move forward when we're talking about calculations. All right, and in Chem 111, we talked about molarity, mass percent, mole fraction. I know you don't remember it, so we're going to go over it. Right, so the first one we talked about was molarity. And for molarity, we're going to talk about it in terms of solute over solution, but more specifically, we're going to talk about it in terms of moles of solute over liter of solution, right? And that's important because if I give you information about the solute and a solvent, you can use that information to come up with an amount of solution, right? But the amount of solution is not equal to just the solvents. We have to be careful there. All right, for mole fraction, all we need to know are the total moles of each component involved in what we're looking at, right? So it's kind of like a fraction. If I said, how many people in here have blue shirts on, right? What fraction? We would talk about a number of blue shirts out of the total number. Somebody can't hear, hold on. All right, can everybody else hear me online? Okay. Thank you. Wonderful. All right, so for mole fraction, it's simply just that fraction. Mass percent, a little bit different. We're going to talk about everything in terms of grams, right? But for this, we're looking at some number of grams of solute over some number of grams of solution times 100%. Okay? There will be times where we change that, right? It might be that I give you the mass percent and we're trying to work a problem, but I don't give you anything about the solute. We can make an assumption there. We can say, okay, if that mass percent is 5%, let's assume it's out of 100, right? And we can work that way and move backwards to find grams. But I'm going to work problems. I'm just trying to introduce you to the concept of working that a little bit differently, okay? All right. Let's just jump right in. All right, so this is determine the mass percentage concentration of a solution prepared by dissolving 3 grams of sodium chloride. I'm going to remind myself that that's the solute. In 150 grams of water. And that is my solvent. Because we're looking for mass percent, we're looking for grams of solute over grams of solvent. Oh, no, solution, sorry. I lied. It's not to mess up. But this is where the information comes in. If I know the mass of solvent and I know the mass of my solute, by default, I know the mass of my solution, right? So the grams of my solute the grams of my solution will be the grams of the solute plus the grams of the solvent. This gives me 1.96%. Feel pretty good about that one? Let's don't stop there. So depending on the class you had for Chem 1, some people may have introduced molality. Some people may not. I introduce molality. Other people do not. So this is a little bit different. I don't like that the terminology is very similar. Molarity, molality, they differ by one letter. So when I'm referring to molarity, you'll see me write a capital M with a line under it. That is very old school, but I like it because it helps me to remember the difference between the two. When I'm talking about molality, I do this little lowercase, somewhat cursive curly QM, right? This was old school again, years ago, whenever I took general chemistry. That's how we distinguish between the two. So for molality, we still want moles of solute the same way we do for molarity. The difference is now we want kilogram of solvent instead of liter of solution. Right? Now, let's think about why that's important. Why would we want to use molality versus molarity? Right? So one of them is definitely, we're talking about the concentration in terms of liter of solution, right? So that's a volume. The other one we're talking about in mass. What if there's a huge temperature change? Is that going to change my information about my liter of solution? Don't we know that a huge temperature change changes volume? We kind of learned that in Chem 111. We're going to go over it some more, right? But that would be a way that we would want to use molality to describe what's happening, you know, with our concentration instead of talking about this volume change, right? All right, determine the molality of a solution. So where you have the same exact values that we had in the last problem. But I need moles of solute, which means I'm going to start with my grams of solute. And I'm going to use the molar mass of the solute as a conversion factor. And do it such that the grams cancel out. This gives me 0.05. Let's see, we're going to do 3 significant figures. So that's our moles of sodium chloride. I can now fill in for moles of solute. I'm going to divide that by kilograms of solvent. Well, I know the grams of solvent. Isn't that an easy conversion to make? If I have 150 grams, can't I just turn it into 0.15 kilograms? Does everybody know how to do the conversion? I'm going to take my decimal and move it 1, 2, 3 places. The other thing you could do is divide by 1,000, right? The actual conversion factor is there are 1,000 grams in 1 kilogram. Gives me a molality of about 0.342. And technically, this is only 2 significant figures, the 150 grams. How could I make that 3 significant figures? Can't I just put a little decimal there? And that decimal says, okay, that 0 is significant, right? We could turn it into scientific notation as well, and that would give us Do we not like significant figures? You'll be glad to know that we don't hold you to them on an exam. Okay, or that we don't test that you identify significant figures. All the answers will have the same number of significant figures. Okay, so this one, it's asking how many grams of sodium chloride must be added to 500 grams of water Yes. Somebody wants me to show the previous example for 2 seconds. It's a little longer than 2 seconds, but is that good? Okay. All right, so now we're taking a certain, or we want to find the number of grams of sodium chloride we need to add to make a certain molal solution. And that molal is going to be 0.75. So if I set up and I know that molality is equal to moles of solute per kilogram of solvent, I can fill in some of this information, can't I? Right? So I have 0.75 is equal to some number we don't know divided by 0.5 kilograms. So I get that X is equal to 0.375. Right? Now, I need to remember what that X is. That X is moles of solute. So now I've got to keep working my moles of solute. That means I have moles of sodium chloride. So now I'm going to say that 0.375 moles of sodium chloride, using the molar mass of sodium chloride as a conversion factor, it's going to give me the number of grams. And that's roughly 21.916. Because we have 2 significant figures, you would see numbers like this as an answer on the exam. And they would all have the same, so you would only see things that have 2 significant figures. All right. So we've looked at molality, molarity, mole fraction, mass percent. Keep in mind separate what you need for each one of those, right? You will have an equation sheet on the exam. It does have information on there about that. It'll have what molarity is, have things like that. But I expect you to know what to do with it, right? So I'm giving you the tools, but I want you to know what to do with it, right? You know, it used to be that we didn't give equation sheets. We'd make you memorize stuff like that. But technology changes. Old people weren't used to it, but you can look that stuff up, right? If you're an engineer and you're out in the field, you're going to look stuff up. You're going to have whatever device with you, you're not going to have to memorize equations, but we want you to know what to do with them, right? So here's a good example. Express the concentration of a 3% peroxide solution as molality and mole fraction. If I don't tell you what the solvent is, in this class, you should assume it's water, right? So, express the concentration of the 3%, so that's mass percent. Right, mass percent is equal to 3%. It doesn't tell me anything else, right? This is where I want you to make an assumption. I want you to assume that we're dealing with 100%, right? So basically, this is going to be equal to 3 grams of peroxide out of 100 grams of solution, right? Wouldn't that be 3%? 3 divided by 100 times, right? So now I know how many grams of peroxide I have. I also know how many grams of solvent I have, don't I? If I have 100 grams of solution, and I take away 3 grams of peroxide, it's going to leave me with 97 grams of water. How do we feel? Right? Okay. So now, in order to do molality, I need moles of solute and kilogram of solvent. Well, I have the kilogram of solvent because I can just turn 97 grams into kilograms. That's easy. But I need moles. So I'm going to start with 3 grams of peroxide. And I'm going to use the molar mass of peroxide. But now I got to calculate that. Don't we remember how to calculate that? Can't we just look at the periodic table? Or if we remember that oxygen is 16, we can say that this is 32. We'll say hydrogen's 1. We're going to forget that 0.008, right? And say that this is about 34 grams. Does everybody remember that, how to look at the periodic table and do that? Okay. So 3 grams divided by 34 grams gives me 0.0882 moles of peroxide. So I'm going to take that value and this value and plug them in up here. And that gives me about 0.909. We feel okay with that one? Okay. Now, mole fraction. In order to do mole fraction, I need moles of peroxide over total moles, which means I need moles of peroxide, but I also need moles of water. I know how many grams of, Haley, the 34 came from calculating the molar mass of hydrogen peroxide. Oxygen is 16 grams per mole, but we have 2 of them. Hydrogen, we're saying, is about 1 gram per mole, but we have 2 of those. All right. So we're going to take the 97 grams of water. We're going to take the molar mass of water, which is about 18. Know that your solvent will always have the larger number of moles when you're doing mole fraction. Some people look at it and say, oh, it can't be that, but it is. So we're going to take these two, and we're going to do mole fraction. So that's going to be 0.0882 divided by the number of moles of the solute plus the number of moles of water. Which gives us about 0.0161 for mole fraction. This is a good time to talk about units. Molality, your units, yes, we give it the little m, but it will be moles per kilogram. Molarity is moles per liter. Mole fraction, there are no units. And the symbol we use for mole fraction is chi, funky X. And for mass percent, there are no units. Right, those kind of cancel out. All right, you guys try this one and then I'll work it with you. So there's a question on the chat that asks if I'm going to post lecture recordings. Yes, they will be in the Blackboard Collaborate link, and you can go in and see the recordings. All right, so this is asking us to find molality and mole fraction. Molality needs moles of solute and kilogram of solvent. Mole fraction just needs moles of everything. But it gives us the mass percent. So, and it doesn't give us any volume, anything else. So that's where we're going to assume this 12% is out of 100 grams of solution, right? As long as we're using the ratios correctly, making that assumption is fine, right? So we're going to take this, and we know that we have 12.5 grams of ethanol. If I have 12.5 grams of ethanol, that means I have 87.5 grams of water. Is that right? Did I do that calculation correctly in my head? All right. So in order to do molality, I need moles of solute. I'm going to start what I was given. I'm going to use the molar mass as a conversion factor. And that gives me about 0.271 moles of ethanol. Kilogram of solvent, easy enough, I just moved the decimal. So now molality is 0.0, not 0, 271 moles divided by 0.0875 kilograms, which is about 3.10. Now, some people would have gotten 3.08. It depends on how you carry your numbers. If you keep all of your numbers all the way through, you get 3.1. If you truncate them along the way, you would get 3.08. I'm not going to give you two answers like that on the exam and you have to choose, right? It's not going to be like that. They're going to be, if it's around 3.1, you're going to be able to identify that answer. All right. So now we're going to do mole fraction. In order to do mole fraction, I need moles of the solvent. So I have 87.5 grams. We know that the molar mass of water is about 18 grams per mole. This gives us 4.86 moles of water. Now, I'm going to write ETOH as a little subscript on my chi. And I'm doing that because we could calculate the mole fraction of water if we wanted to, right? So we want to be very specific as to what this answer is going to be. And we are going to calculate the mole fraction of ethanol. So that's going to be the moles of ethanol divided by the moles of ethanol and the moles of water. That gives me a mole fraction of approximately 0.0528. All right, so we've been converting between different units or different concentrations. Now, let's convert one that requires a little more information, right? If I want to convert between molarity and something, depending on what I've been given, I may need density to do that, right? Because molarity involves liters of solution, right? And I've got to work backwards from that. So here, calculate the molarity. I'm going to remind myself. I do this, it seems like I shouldn't have to, but I do this every time. Moles of solute per liter of solution. I've been given that I have a 12% sulfuric acid solution. I lost my little sig fig in there, but it's there. 12%. I have the density, but I don't have anything else, right? So I know that that 12% means that I have 12 grams of sulfuric acid per 100 grams of solution. And that's all good and fine. If I were going to molality, all I would have to do was figure out the mass of the solvent, but that's not where we're going. We want to get to liters of solution. So I've got to take this and change it to liters of solution. I'm going to use density, right? Density of that solution specifically is 1.080 grams per milliliter. So let's start with 100 grams of solution. I'm going to use the density as a conversion factor, and I have 1.080 grams per milliliter. That gives me 92.59 milliliters. I'm still not to liters though, am I? Right? But the easy way to do that is just divide by 1,000. Or move my decimal 3 places. So I have my liters of solution. I now need moles of solute. So I have 12 grams of sulfuric acid. I have the molar mass. They gave it to me. Let's turn off autofocus. See if that helps. And that's 98.08 grams per mole. And that gives me 0.1223 moles of sulfuric acid. So now I can just plug it in. The right way. And that gives me about 1.32 molar. All right, so for this problem, just this problem, Krish? Okay, asking for a recap. All right, so for this problem, it's asking us to calculate molarity, but the only thing it's given us is the mass percent. So I have to take from mass percent what I can and work towards molarity. It helps if you remind yourself what you're looking for, right? You need moles of solute, liter of solution. So the mass percent tells me I have a certain mass of the sulfuric acid, and I'm assuming 100 grams of solution because it doesn't give me anything else. And that's completely fine to do, right? Because once we move away from that, we're working with ratios, and all we're looking for is concentration, so it's going to work out just fine. So because I have the grams of solution, I have to have, without a doubt, the density of that solution in order to go to volume. There's no other way around it. They give us the density, so I use the 100 grams of solution, I'm assuming, with the density of that solution to give me the volume of that solution. I can then convert that milliliters to liters And that's what I will actually plug in for my molarity. 12 grams of sulfuric acid, I can simply convert to moles and then plug that in for moles to get my final answer. All right, but what good is this? We got all this stuff. What does it really mean, right? What are we doing with it? Well, we're going to talk about solubility, and we're going to look at different reactions, and we're going to determine whether that reaction produces something that's soluble or not. You're going to have to think back to those solubility rules that we had in Chem 111, but not too much, where we kind of give you hints as to which of your products will be insoluble. But let's talk about the terminology. What does solubility really mean? What are we looking for? Well, if we want to know how soluble something is, that means we want to know how much of it we can actually put into solution, right? So the solubility is the concentration of that solute that can exist in solution with excess of it, right? So let's think about, have you ever in Chem 111, I don't know if they let you make your own solutions or not, but if you're putting salt in water, it has a specific solubility value, and it's different for different temperatures, but we're not going to go there. So you can only put so much in solution. Once I've dissolved as much as will go in solution at that temperature, any more I put in there is just going to sit on the bottom, right? So that, by definition, is what we mean when we're talking about solubility. If something is saturated, right, then it is equal to its solubility. If I say I have a saturated solution, the concentration of that solution is exactly equal to its solubility, right? If I have something that is unsaturated, obviously, it's less than the solubility. If it's supersaturated, it's greater than the solubility and very unstable. Typically, what happens with a supersaturated solution is it all crashes out. All you have to do is move the beaker. You give it some sort of outside force, and everything just falls out of solution. So let's talk about that process. If I want something to dissolve in solution, I first have to separate the solvent particles. I have to separate the solute particles. Then I have to allow it to come back together such that the solvent and solute are interacting, right? This requires energy on my part, or on the reaction's part, not necessarily mine, right? So it requires energy to separate those molecules, right? Because you think about it, water molecules aren't going to want to separate from water molecules. They're very happy together. We've got to have some sort of energy inserted to separate those. When they come back together, it gives off energy. Do you remember from Chem 111? Yeah, the slide tells you the answer. But do you remember from Chem 111 the type of reaction that requires energy and the type of reaction that gives off energy? Do we remember that? Think about the thermite. Anybody use the thermite reaction as an example? Or any kind of combustion, right? That's an exothermic reaction. No energy required, it's just going to happen, right? So these are endothermic, and this is exothermic. The amount of energy required at each of those steps will determine what the overall reaction is, right? So we have endothermic steps that require energy, and that is separation of the solute and the solvent. then they come back together, right? If where we end is less than where we started, meaning a lower energy than where we started, right? That is exothermic. So if the coming back together gives off more energy than we had to use, that's an exothermic overall solution. If we end, meaning we give off less energy than we had to use, then we have an endothermic solution. And we're going to talk more about this. So, typically we say that exothermic reactions are spontaneous. They just happen. No outside force necessary, right? Kind of like a ball rolling down a hill. We don't have to do anything to it. But there are endothermic reactions that are also spontaneous, which means something else is going on, right? We can't just say that all spontaneous reactions are exothermic, because that's not a true statement. Remember that whole, did you take logic? I hated that class. But we can say that all exothermic reactions are spontaneous. That's a true statement. But we can't say that all spontaneous reactions are exothermic because there are some endothermic. Let's talk about why. Well, if we look at the specific reaction of ammonium chloride, and this is a solid that breaks up into an aqueous solution in water, right? We are going from a solid to aqueous. What have we done there? We went from something stagnant, static, not moving, to something that can move around, right? So we've kind of increased disorder. Wouldn't we say that a solid is extremely ordered? Wouldn't we say that a liquid or aqueous is somewhat disordered? What would we say about a gas? We'd say extremely disordered, right? It can move all about. So that's another way to look at a reaction and determine if it's going to be spontaneous. Right? So this is just an example, and I wish I had it in PowerPoint where I could show you. So basically we have two gases. They're separated by a glass wall. As soon as you, what do I know? If I opened a bottle of perfume up here, or is the gas, the fumes, are they just going to stay in the bottle? Eventually it's going to run us out of this room, right? It's going to go all the way to the back, because that's what gas molecules do. They want to expand to fill the size of the container. So here we have these two ordered gases, one gas, one gas. As soon as we move that glass wall, they expand to fill the entire size of the container, and they mix spontaneously. We don't have to do anything to it, right? So spontaneous prefers disorder. So a spontaneous reaction will happen as we move from something ordered to disordered. We're going to look at what that means. So if I have going from a solid to a liquid or an aqueous to a gas, this is increasing disorder. It is also called increasing entropy. Okay. We're going to talk about what that means. All right, so if I want to mix different solvents together or different solutions together, can I just mix anything together I want and they're going to mix perfectly? I can't mix oil and water, right? We know that things like that don't mix. But what determines how well they are miscible? How well do they come together, right? If you remember at the end of Chem 111 or Chem 1, whatever the number was, you should have talked about intermolecular forces and like dissolves like. Did you talk about that? Yeah, I kind of know, don't care. Sleepy. All right, so we're looking at the different intermolecular forces, and let's talk about some of them. We have London dispersion forces. We have van der Waals forces. We have dipole-dipole. We have hydrogen bonding, right? And we can look at two substances that we want to bring together and determine how well they are going to mix. We typically talk about it as how well the solvent will dissolve the solute, right? Note when I say dissolve, I can dissolve a gas in a liquid, I can dissolve a liquid in a liquid, and I can dissolve a solid in a liquid, right? So it doesn't just mean I'm dissolving a solid in a liquid, right? We typically think of Nesquik, right? Chocolate powder and milk, or what was that other stuff? I don't even know. Crystal Light in water, whatever, right? We typically think of putting a solid in there, but they have that new Mio drops or whatever, right? In that liquid in liquid, right? Think about your sodas that you drink. Any kind of carbonated soda that has gas dissolved in the liquid. So when I talk about dissolving, I'm not specifically talking about solid and liquid, okay? So we say that like dissolves like. This is true no matter what. So the more intermolecular forces they have in common, the more likely it is to dissolve, right? So if we have, let's talk about, these are our intermolecular forces, right? If I'm talking about a dipole-dipole, I'm usually talking about something that is polar. If I'm talking about hydrogen bonding, I'm talking about something that is probably polar and that probably has H bonded to a nitrogen or H bonded to an oxygen, sometimes H bonded to a fluorine. When we talk about London dispersion forces, we're really talking about nonpolar, van der Waals nonpolar. Now, does a polar molecule have London dispersion forces? Absolutely. Everything does. But if that's the only thing it has, then it's probably nonpolar, right? So as we go through, we're going to identify solubility here. We're going to look at it in terms of what properties, what intermolecular forces do each of these have in common. All right, so let's look at this first one. We have iodine, and we're asking, is it more soluble in water or in hexane? Well, first of all, iodine. Is that polar or nonpolar? I would say nonpolar, right? If we had IF or ICL, then we would say it's polar because they are different. Well, let's talk about these two. Water. Don't we know that's polar? Can we just write that? Hexane. Even if you don't know what hexane means, we know it's just a bunch of carbons and hydrogens. Would we say it's polar or nonpolar? Nonpolar. All right, can we stop there for this one? Can we just say that iodine is going to be more soluble in hexane? We don't even need to go any further, because does iodine have hydrogen bonds? Is there an H anywhere in there? All right, so let's look at the next one. We're asking if methanol is more soluble in water or hexane. Well, just by drawing this, I don't know why I put an extra C in there. Just by drawing this, we know that we have hydrogen bonding, don't we? We have hydrogen bonded to an oxygen. So here we have hydrogen bonding. Here we have hydrogen bonding. We don't have hydrogen bonding there. This is polar. Water is polar. This is nonpolar. Right? So wouldn't we say that methanol is more soluble in water? All right, do you get the feel of intermolecular forces and how we're going to look at them? Okay. Now, in here, we're going to talk a lot about ionic compounds. And when we talk about ionic compounds, we're really talking about dissolving a solid in water and seeing how many of those ions will go into solution, right? So we talk about it in terms of solvating, right? So basically, we're going to take sodium chloride, which is an ion, dissolve it in water, and we want to see how much we can get solvated, meaning how much will be in solution. Okay? I'm not going to read the slides to you. Y'all can read those parts. All right. This process is the same as dissolving when we talk about separating the solute molecules, separating the solvent molecules. This is what we use. We use that same process. And you've got to separate your ions. When you separate ions, you go from solid to aqueous, right? We're increasing disorder. When you separate the water molecules, we are also increasing disorder. When we hydrate them, right, we're decreasing disorder because we're restricting them again, right? So we can kind of look at it in terms of enthalpy, right, where it requires energy, then it gives off energy. I didn't see the hand, I'm sorry. What was the question? Did somebody have a question? online. All right, I'm gonna keep going and I'm gonna keep looking for the hand. I'm gonna hire somebody to read the chat for me. Oh, yeah. So we can look at it in terms of enthalpy and entropy here, right? Because we can look at it in terms of how much energy is required or how much energy is given off. Or we can look at it in terms of entropy or disorder, right? Meaning, have we created disorder, or have we increased disorder, or have we decreased disorder? Right, so here's another one. Potassium chloride, that's an ionic compound. This one, you better say water every time, right? Ionic compounds are extremely polar, right? The most polar you can get because they are ionic. Right? So, this in a nutshell is where I was going with describing it in terms of enthalpy and entropy, right? When the universe aligns. Now, when we talk about a solution, remember I said we used molality versus molarity when we're talking about temperature change because we don't want to have to deal with the change in volume, change in everything. Well, pressure, if you think about it on a solid, right? Even a liquid really it can be compressed, but not as much as a gas, right? When we're talking about pressure change, we're really talking about the effect it has on a gas substance, okay? We know that if we compress a solid, we're not going very far. We can compress a liquid only so far, but a gas we can take from the gas in this room and compress it to a very, very, very small quantity or volume. So Henry's law helps us look at that in terms of solubility of a gas in a solution, right? And says that the solubility of the gas is directly proportional to the partial pressure of that gas, right? Anytime we have a proportionality, we have to have a proportionality constant. So concentration is equal to some proportionality constant times that partial pressure. This happens to be Henry's law constant. Notice that it's using molality as the concentration, right? That way we don't have to worry about a change in that concentration based on the change in pressure. All right, so the example says that water at 20 degrees Celsius, I might not need that information, but I'm going to write it down just in case, is saturated with air that contains CO2 at a partial pressure of 8 torr. What is the molal concentration of CO2 in the solution? Well, we're going to use the Henry's law. And because the temperature said 20 degrees, we're going to look at 20 degrees. So we're going to use 3.91 times 10 to the minus 2. And that is molal per atmosphere. I encourage you to write the units for everything you do. If you don't write the units, you will miss some sort of conversion that might be necessary. You might put the answer in the wrong, whether it be kilojoules, joules, liters, milliliters, whatever. Here, it's going to show us that we need to convert the torr to atmospheres, right? Because if I have atmospheres here and I have torr there, it's not going to cancel out. So I'm going to take 8 torr. The conversion factor, which is also going to be on your equation sheet, is 760 torr for every 1 atmosphere. That gives me 0. Now I'm ready to solve the problem. Concentration is equal to Henry's law constant times the partial pressure of CO2 in atmospheres and that gives me 4.1 times 10 to the minus 4th molal. Let's do one more slide and then we'll take a little break. How about that? All right. So if I'm looking at going from A to B, and we're going from a solid to aqueous, right? There are 2 ways that I can look at this. I can look at it in terms of being endothermic or being exothermic. So let's say that this is an endothermic reaction. That means I need to add heat as a reactant, right? So if delta H is positive, that is endothermic. That means heat is a reactant. Now, with this, let's pretend we have this little balance going on. It is completely balanced. But if I increase the temperature, what I'm doing is increasing the effective concentration of the heat. And when I do that, I get an imbalance, right? How can I fix this imbalance? Don't I need to make more B? Right? Let's think if we're talking about these in weights. In order to fix this seesaw, don't I need to put more weight where B is? The only way to do that is the reaction goes forward. Right? So, the solubility increases with increasing temperature if we're endothermic. And this is why, right? Because when I increase this concentration of heat, I force the reaction to go forward. And if I'm forcing the reaction to go forward, aren't I dissolving solid and making aqueous B? Right? As that reaction goes forward to me, forward to y'all. As that reaction goes forward, I'm dissolving A and making B, right? So I'm increasing the solubility. Does that make sense? Kind of? No, don't care. Well, I'm going to show you the opposite way too. So if I have that same, so when I say the reaction goes forward, it means it's going from A to B, right? So the reaction goes forward, it goes from left to right. If I said it goes reverse, it would go from right to left. Does that make sense? So if we have this same reaction, but it's exothermic, it means that heat is a product. Again, I've got my little visual aid. If I increase the temperature, I'm still increasing the effective concentration of heat. But this time, it's imbalanced so that I need to go in reverse, right? So now the reaction goes reverse. So for the exothermic, we are going to precipitate A, but for the endothermic reaction, we are going to dissolve A. So we say that solubility decreases if we increase the temperature for an exothermic reaction. So typically, if we increase temperature, we increase solubility. We've heard that all through Chem 111. And it's true. And when we look at this, we see that it's true. Almost all of these, except for little guy at the bottom. We can probably say that that is an exothermic reaction, right? And that by increasing the temperature, we're decreasing the solubility. All right, let's take a break. How long of a break do we want to take? 5 minutes, 10 minutes? Let's do 10 minutes. Y'all stretch, go to the bathroom, do what you need to do. And then we will reconvene and we will talk about colligative properties. Yes? Sure. Okay. Hopefully everybody's back from the break. Now we're going to talk about everything that we've talked about up to this point, but we're going to apply it to colligative properties. And when we talk about colligative properties, we're talking about properties of a solution that change in proportion to a change in concentration of solute particles, right? So as we increase or decrease solute, what happens to these properties? And the first one we're going to look at is vapor pressure. If we think about a given solution that has a specific vapor pressure, that means that we're looking at the amount of molecules that move up into the vapor phase, right? And if we add some solute in there, let's say we're adding sugar, right? And we know that water has some sort of vapor phase that water molecules can move up into the vapor phase. If we add sugar in there, these blue molecules, we are blocking some of that surface. So we're not allowing as many water molecules to move up into the vapor phase. So by increasing solute concentration, we decrease vapor pressure. Right? So you can think about it in terms of as we're moving from evaporation to condensation. We're talking about water, right? This is a dynamic process, meaning it's at equilibrium, meaning the amount of molecules that evaporate is equal to the amount of molecules that condense, right? We can take vapor pressure and talk about it in terms of Raoult's law. And we're going to look at the pure vapor pressure of a solution versus the partial pressure or pure vapor pressure of a solvent versus the partial pressure of that solvent after we've added something to it. So when we look at it, we can talk about this in two ways. We have the partial pressure of the solvent plus whatever we've added, right, is equal to the pure vapor pressure of the solvent times the mole fraction of the solvent. Right, that solvent plus just means I've added something in there. Right, it's no longer a pure solvent, so we're talking about it in terms of a partial pressure. But I can also talk about it in terms of how the pressure has changed. And I can take the change in pressure of the solvent is equal to the pure vapor pressure of the solvent times the mole fraction of the solute. Right? And let's think about what we're doing here. We're taking mole fraction, which is how many solute particles per the total we have, and we're multiplying that. So that's kind of like our proportionality constant, right? That's telling us how pure solvent vapor pressure relates to the partial pressure. So this one says at a temperature of 27 degrees Celsius, Sometimes I go ahead and convert that to Kelvin. The vapor pressure of benzene, so that tells me it's the pure vapor pressure of benzene, is 104 torr. It wants me to calculate the pressure of benzene, right? What is the vapor pressure of a solution that has 0.1 mole naphthalene dissolved in 1.9 moles of benzene? So here we're going to do that benzene solution, right? In order to calculate that, I need the mole fraction of benzene, and I need the pure vapor pressure of benzene. Well, the pure vapor pressure is there, we're good. I now need to calculate the mole fraction of benzene. It gives me everything I need. It gives me the moles of benzene and the moles of the solute that's added, so I don't have to do any kind of calculations there. But if I'm calculating the mole fraction of benzene, then I need 1.9 divided by 1.9 plus 0.1. So the mole fraction of benzene is 0.95. So now I can calculate the partial pressure of benzene with stuff added to it as being 0.95 times the total pressure So I put the plus sign down here because this is no longer pure benzene. This is benzene with the naphthalene added to it. Does that make sense, Mary? All right, so if this had asked how much it was lowered, right? Technically, we could just say 104 minus this and come up with that change, but we could have also used this, right? Which just means that I would have had to calculate the mole fraction of the naphthalene, right? Does that make sense? Because this one, I would have used the mole fraction of the naphthalene and the pure vapor pressure, and it would have given me a change. Let me ask you this. If I know that this is the mole fraction of benzene, and there are only two components in there, can I easily come up with the mole fraction of naphthalene? They have to be equal to 1, right? So I can simply say that the mole fraction of naphthalene is 0.05. All right, so over here, if I said 104 minus 98.8, we should get 5.2, something like that. That's all right. All right. And if I plug in over here, I should get 5.2. Right? So there are two ways you can do it. Both of these equations will be on the equation sheet. It depends on what you're being asked. But like I said, going the long way and then subtracting to get your answer is just as easy as doing it the other way. 0.95 times 104. Did I get that wrong? Check my math because, no, that's right. Check my math. I'm just as tired as you are. So for this one, because it's asking for the vapor pressure, the answer is 98.8.
Okay, so in what case would you use the 0.05?
So the only time you would use that is if you're looking in for the change in vapor pressure, or if it were asking for the vapor pressure of naphthalene. Does that make sense? Okay. All right. So we know that as we increase the solute concentration, we decrease vapor pressure. We're now going to look and see what we do to boiling point. The description of this should tell you what's going to happen to boiling point, right? Because if we're at 1 atmosphere and we're talking about raising molecules into the vapor phase, we know that water boils at what temperature? 100 degrees Celsius, right? That's at 1 atmosphere. If I change something, if I add solute in there, what I've done is lowered the vapor pressure, which means I have to turn up the heat in order to get those molecules to move back up into the vapor phase. So it's boiling point elevation. If I add solute in there, I have to heat it up to a lot higher temperature to get it to boil. Does that make sense? All right, and so if we look at, right, if we look at this plot, here we have different concentrations, right? And the concentration is increasing. So this is going to be the highest concentration of solute that we've added. So the first one, right, is going to have a boiling point of about 80 point something degrees. But as I increase the temperature, right, we're talking about this 1 atmosphere line is where we consider the vapor phase and moving up into the vapor phase. We're talking about at 1 atmosphere. So as I continue to add solute, I continue to increase the boiling point of that solution, right? It's proportional. The more I add, the more it's increasing. We can look at this because we know that the change in boiling point is going to be proportional to the concentration of the solute. We have a proportionality constant, which is the boiling point constant. I'm going to go ahead and introduce another variable here. It's an I. It's called the Van Hoff factor. Right now, we don't need it because we're not talking about adding ionic solutions, right? So I, for a non-electrolyte, is going to be equal to 1, right? So we can kind of just ignore it here. But it is part of the equation because if we're using ionic solute, we got to worry about it. All right. We can apply the same concept to freezing point depression. What this means is the more solute I add, the more the temperature has to drop to get that solution to freeze. So during the winter, not around here because we don't have a lot of ice on the roads, but during the winter in places where there's a lot of ice on the road, they have salt trucks and they spread salt on the road, right? A lot of people think, oh, the salt is to melt the ice. Not true. What that's doing is it's putting a layer of salt so that during the day, when the ice does melt, it creates a salt solution, and then at night, the temperature's got to drop a lot colder in order to get it to refreeze, right? So anybody that goes to the beach with a cooler and you want the cans to get really cold, if you put salt in the cooler with your ice, you're going to, in a sense, make that water a lot colder. So, does that concept sound right now? Right? How many people thought the salt was melting the ice? A lot of people do, and you know, and it might to a certain extent. You're putting something on the ice, you're probably going to melt it. But the whole concept is so that it doesn't refreeze at night. All right, so same concept. The change in freezing point is proportional to the concentration. But this is what we want to remember. And we're still going to have that I in there. Here we go. Don't know why they have to use such big words. Benzophenone freezes at 48.1 degrees Celsius. So here we're talking about two different temperatures. And we know that the equation we use for this talks about a change in temperature. So I have what is an initial temperature. And then I have a final temperature, right? So I'm going to skip this middle part for just a minute, right? Because we're adding some stuff, and it forms a solution that freezes at 42.4 degrees Celsius. We have 1.05 grams of urea and 30 grams of benzophenone. It wants us to calculate Kf. Urea is a non-electrolyte. So I is equal to 1, so we can kind of just drop it off and forget about it. Now, if I have TF minus TI, I'm going to get a negative value. I'm just going to tell you that in Kelvin, you don't have negative values, right, in temperature. And we can't have negative values in concentration. And our KF, if you remember, are not negative. So we're going to take the absolute value right? And that makes life much better. Well, I can plug the temperatures in. I have my grams of benzophenone, which I can turn into kilograms, right? Because I'm using molality. But I now need to turn the grams of urea into moles, right? So I'm going to take 1.05 grams of urea. I'm going to use the molar mass of urea. And that gives me 0.01748. For me, I'm going to rearrange this equation first because I want to have what I'm solving for on a side by itself. So now I can just plug in. So I have my final temperature minus my initial temperature. And I'm using degrees Celsius because my KF units is in degrees Celsius per molal, right? So I'm leaving it in degrees Celsius. Molal is going to be moles of solute per kilogram of solvent. And I get roughly 9.78 degrees Celsius per molal. How do we feel about that? One thing to remember with freezing point is that I'm not going to talk about initial and final here, but I'm going to say that the original freezing point is always greater than the new freezing point. Right? Because it's freezing point depression. So just keep that in mind. So if you end up with a negative, you can probably just drop the negative and you have the right answer. All right, you guys try this one and then I'll work it with you. All right, how are we doing? Pretty good? All right, so this is very similar to the last one, it's just asking for a different outcome. So it says benzophenone freezes at 48.1 degrees Celsius. So that's our initial freezing point. It has a freezing point constant of 9.8. Then it says we have a 2.5 gram sample of solute. That solute has a molar mass of 130 grams per mole, so we don't need to know what it is. But it's dissolved in 32 grams of benzophenone. It wants us to calculate the new freezing point. All right, so I have TF minus TI is equal to KF times moles of solute per kilogram of solvent. Right? Well, I know all of these except for moles. I need to do a little calculation here. I'm going to take the grams of solute, divide it by the molar mass of the solute, and that gives me, could just do it in one, right, put it in there all together, but let's just find a value. 2.5 divided by 130. So now I have 48.1 minus TI is equal to 9.8 times the number of moles divided by the kilograms. Point 0.0192 divided by 0.032. I'm going to multiply that here. So now I get 48.1 minus TI is equal to 0.588. What do I do now? So let me ask you this. This is, right, this whole absolute value thing kind of throws people off. But if I know that this is the larger value, instead of writing it like this, could I just write it like this? Couldn't I do that? Doesn't that make more sense? So in my mind, for freezing point, I always write TI minus TF, so I don't have to throw in that absolute value. That's why I wrote in there that TI is always greater than TF for freezing point. So now we're good, right? Oh, yeah. I did do that wrong. I did this backwards. Did y'all see that? Thank you, Elena. So on here, I did this backwards. I wrote 48.1 for the final, and it's not, because in my mind, I always write it first, so I screwed up. Thank you. So here, it should have been written TI minus 48.1. I'm going to do it with a pen that'll actually see. Does it make sense what I did? Sorry, guys. Yes, is TI. But okay, TF. But yes. Whew, we need another break. Too many errors here, right? So here, again, it should be written this way. So it's too messy. I'm getting too messy. So it should be TF minus 48.1. When I switch it down here, it should be, as I write it without these guys, if I wrote it the other way, right, it would be TI, which is 48.1, I want to say bad words right now. I'm going to pull out a piece of paper and write it neater in a minute. Yes. Oh, no, it's you. It's me. This is 5.88. Is that what you got? Yep. So let me pull out another piece of paper because this is terrible on all levels. Okay. Here we go. I'm going to write it neatly so everybody can see. But I'm going to leave this. I'm going to scan this so y'all see that I screwed up. All right. So again, when we write it, we have delta T freezing is equal to the freezing point constant times the molality. We know that we're not talking about something ionic, so we're going to ignore I right now because I would be 1. So then I know that I can take this delta TF and I can turn it into T final minus T initial. But if I do that, I have to take the absolute value of it. Right? Because in my mind, I know that TI is always larger, and we're only looking for the difference. I prefer to write it like this. So now I know that my initial temperature is 48.1. We don't know the final. That's what we're looking for. KF is 9.8. Now, for molality, I can turn it into 2.5 divided by 130, all divided by 0.0320. Right? I did this math on top. Is everybody okay with that? Okay. So now, let's see if I can do my calculation correctly. I have 2.5 divided by 130. I'm going to divide it by 0.032. And I'm going to multiply it by 9.8. I carried all my numbers. It'll work out. So now, if I want to solve for TF, because this is minus TF, I'm going to have to move TF over here and the 5.89 to the other side. It's algebra. So it's roughly 42.2 degrees Celsius. Is the new freezing point. Right? So however you want to do it. If you want to stick with your absolute values and do it that way, that's completely fine. I prefer to do it the other way, which is why I screwed up on the calculation. All right. We're not done with colligative properties yet. We will sum them up when we're done. We're now looking at osmotic pressure. It's another colligative property. When we're talking about diffusion, we're talking about taking a solution through some semi-permeable membrane. That's where we experience osmotic pressure. So, we have molecules that want to move through the membrane and molecules that can't. And those molecules that can't, the more we add, the higher that pressure goes because they block the movement of the molecules that can move freely through the membrane, right? So it's kind of like people standing in a doorway when you're trying to get through, right? They're blocking your access, which is creating pressure. So we say that an increase, in this case, we're looking at molarity, is equal to an increase in osmotic pressure. And this is directly proportional. They are directly proportional. Now, when I look at this, this is very reminiscent of PV equals nRT, right? This is pressure. RT. The only thing left is moles and volume. Over here, molarity, which is moles and volume. So if I rearrange this, and we have pressure is equal to N over V times RT, we basically have the equation for osmotic pressure. Right, so just to remind myself, I'm going to write down the possibilities, because if I write it this way, it will remind me that that's a possibility. So here I have a sample of protein that is 5.7 milligrams. We're going to talk about that in terms of grams in a minute. But I have 5.7 milligrams, and it is dissolved. So that means that's the solute in water to give a total volume of solution of 1 milliliter. Right? Well, there are 1,000 milligrams in a gram. So if I divide 5.7 by 1,000, or I move the decimal 3 places, the same thing for milliliter. There are 1,000 milliliters in a liter. it wants me to calculate the molar mass of the protein. Whoa. Molar mass is grams per mole. If the solution has an osmotic pressure of 6.52 torr at a temperature of 20 degrees Celsius. I've got to evaluate everything I have. Remember that R is a constant. So we're going to go ahead and write R because it's very important. It has specific units that we have to take into consideration. It's 0.0821 liters times atmosphere per mole times Kelvin. That means this needs to be in Kelvin and this needs to be in atmospheres. How do we go from Celsius to Kelvin? We add 273. Right? How do we go from torr to atmospheres? Remember, there's 760 torr in 1 atmosphere, so we're going to divide by 760. That gives me so using this, oh, not that's a times. That should be a times 2. So using this, I have R, I have T, I have osmotic pressure, and I have a volume of solution. So we're going to solve for moles. Just rearranged it. So we're going to have osmotic pressure times the volume divided by the gas constant times the temperature. And we should get 3.57 times 10 to the negative 7 moles of protein. So now I'm going to take moles of protein and grams of protein to calculate the molar mass. Grams. Just making stuff up now. So I get roughly 15,980.79 grams per mole. Well, that's a lot of significant figures right there. So if we were leaning towards significant figures, we'd have to look up here and see that here we only have 2 significant figures. Well, maybe if we put a decimal point there, right? But the rest of them have 3, so let's just ignore the temperature and go for 3. So that means that I only need to use 3 of these numbers. So I'm going to have 1.60 times 10 to the 4th grams per mole. Right? So if this were a problem on the test, you might see all of the answers in scientific notation. Don't let that throw you off if you get this number, right? All right, you guys try this one. Okay. So this gives us the molar concentration. It tells us the amount of solute. And it tells us the total volume. and it wants us to calculate the molar mass. Osmotic pressure. Molarity is moles over liters. We don't even really need the osmotic pressure, do we? It kind of told us that this is the molarity that came from this experiment. Go use it, right? So all we're going to do is say that 0.0021 is equal to some number of moles over 0.002 liters, right? So basically what I'm doing is saying 0.0021 moles per liter times 0.002 liters is going to give me the number of moles that we have. So we have that many moles, we have that many grams. And that gives us roughly 2238 point some number of grams per mole. If this were a problem on the exam, we would look and we see that there's two significant figures. So we would probably turn this into 2.2 times 10 to the third. We're feeling pretty good. All right. We're going to sum it up here for colligative properties. Then we're going to talk about colligative properties when we're dealing with ions, where we have to take into account that I, or the Van Hoff factor. So again, just like the concentrations, we're looking at this in terms of what we need to answer these. So when we're talking about vapor pressure, we're dealing with mole fraction. Boiling point, elevation, and freezing point depression. We're talking about molal concentration. And for osmotic pressure, we're talking about molarity. All right, so when the Van Hoff factor comes into play, what we're really looking at is how many different types of ions are floating around out there, right? So if we have sodium chloride, we break up into only 2 ions. But magnesium bromide, we have 2 of those bromides and 1 magnesium, so we have a total of 3 ions. So the number of ions that your ionic compound breaks up into, that's your Van Hoff number. Now, that's a cheating way of calculating the Van Hoff factor. We're not going to do the math to calculate the true Van Hoff factor, right? But this will give us what we need. So we're only going to look at it in terms of osmotic pressure and freezing point and boiling point. Those are the only ones that we will apply the Van Hoff factor to. This is a typical way that we ask a question about the Van Hoff factor. Here we're looking at aqueous solutions, which means that the solvent is water, right? If we're talking about boiling point, then the KB refers to that of water, not your solute, right? So every one of these that we're going to look at has the exact same KB, okay? So here I have urea, sodium hydroxide, barium chloride, and iron nitrate. The concentration of urea I'm just kind of rewriting them for us. Now let's talk about I, because this is the concentration, the Van Hoff factor. Urea is a non-electrolyte. What did we say the Van Hoff factor was? 1. What about sodium hydroxide? Remember, hydroxide is a polyatomic ion, so it is one ion, right? So sodium hydroxide breaks up into a sodium and a hydroxide. So its Van Hoff factor is 2. Barium chloride, Van Hoff factor 3. And iron nitrate, nitrate is a polyatomic, right? That nitrate stays together, and there are 3 of them and only 1 iron, so the Van Hoff factor is 4. Now, this problem is asking us to arrange them in order of increasing boiling points. All I need to know is what the change in boiling point is. The change in boiling point is KB times molal times I. If they all have the same KB value, I don't really need to factor that in, right? All I want to know, this is all relative. We're not asking for specific values. I'm asking you for smallest to largest, right? So water boils at 100 degrees Celsius. I just need to know what the change is to know which one of these is the highest, next highest, etc. So I'm going to take these and multiply them together, right? If I then multiply them all by the same value, it's just defeating, right? We're doing the same thing. So I simply multiplied the molal concentration times the Van Hoff factor. Now I know that after 100 degrees, the next one is going to be sodium hydroxide. The next one is going to be urea, followed by iron 3 nitrate, followed by barium chloride. Does that make sense? Let's talk about this in terms of freezing point. If I were talking about decreasing freezing point, aren't we doing the same thing? Isn't this going to have the lowest freezing point? Yeah, right? If I increase solute concentration, I decrease vapor pressure, I increase boiling point, I decrease freezing point, and I increase osmotic pressure. All right, so this is also, I guess we would turn these around the other way, right? This is also for decreasing freezing point. But we would turn the little alligator things the other way. You couldn't see when I was writing. All right, let's do another one. Practice makes perfect. Okay, so this is different. So this says that water freezes at 0 degrees Celsius. I think we already knew that, right? But that's a temperature. And that's our initial temperature for freezing point, right? It has a KF of 1.86 degrees Celsius per mole. We have a 3.5 gram sample of sodium chloride. It is dissolved in a 50 gram sample of water. Calculate the freezing point. Well, we need to remember that we have to take into account the I, Van Hoff factor. And because we're using sodium chloride, the Van Hoff factor is going to be 2, sodium and a chloride. I also need to calculate moles of solute. And I'm going to do so using the molar mass or the formula mass of sodium chloride. I'm just going to do 23 plus 35.5. That gives me 0.0598 moles of sodium chloride. I can now plug in, and I'm going to take the initial, or not for freezing, yeah, for freezing, I'm going to take the initial, and I'm going to subtract from that the final, because that's what we're looking for, right? We're looking for the freezing point of the solution, is equal to KF times molal, which is going to be 0.0598 divided by kilograms times the Van Hoff factor. So I have 0.0 minus TF is equal to 4.45. So TF is equal to I will tell you that on standardized exams like the MCAT, be careful because they'll give you a question like this and they will give you that your constant, instead of being in degrees Celsius per molal, will be Kelvin per something, right? And you don't pay attention and you just go right for it. So be careful. Always look at your units on standardized exams. The MCAT loves to throw those in there and trick you. Now, here's where we're going to take the Raoult's law and we're going to look at vapor pressure. But instead of taking something volatile and throwing a non-volatile in there and seeing how we change it, we're going to have a mixture of volatile solutions. So we're going to have to take into account two things happening here, right? So typically, when we have this combination of solutions, we're going to look at it in terms of each component separately. So here, according to this diagram, which is very blurry, okay. So if we look at this, we can say that, let's say A is benzene and B would be toluene, right? We could do some calculations for each one of those components, but we want to know what's happening with them together. So I'm going to write everything, even though I don't need it. We have 27 degrees Celsius. And it says the vapor pressure of carbon tetrachloride is 127 torr. Then it says, and that of chloroform is 212 torr. So I have their pure vapor pressures. It wants to know what is the partial pressure of each substance and the total vapor pressure. So I want to calculate the partial pressure and the total vapor pressure that is above a solution if we have 0.4 moles of carbon tetrachloride and 0.6 moles of chloroform, right? Well, in order to calculate these, I need mole fraction and the pure vapor pressure. Right? If I have a bunch of moles in a container, a bunch of moles of gas, when we were doing mole fraction, couldn't I add all of those up to get total moles? Right? Isn't that how I got total moles? Whatever was in there, added them all up. We can do the same thing with pressure. So in order to get the total pressure, we're going to add up all of the partial pressures. Luckily, there are only 2. So the first thing I need to do is calculate the mole fraction. Well, the mole fraction of carbon tetrachloride is going to be 0.4 divided by 0.4 plus 0.6 makes life easy. The mole fraction is just 0.4. I'm going to do the math for the other one, but obviously it's just going to be 0.6. So now I can calculate the partial pressure of carbon tetrachloride. It is going to be 0.4 times the pure vapor pressure which is 50.8 torr. And we can calculate the partial pressure of chloroform, which is going to be 0.6 times the pure vapor pressure Comes out really close to the vapor pressure of the other one. All right, so I've calculated this. Now I just need to calculate the total vapor pressure. I just summed these two. How do we feel? It's going to be a lot of chemistry in 12 days. All right, so with this one, somebody said definitely rewatching the lectures. That's good. I will scan these and put these up as hard copies too. All right, so for this one, if you remember here, we're talking about the mole fraction in solution, right? So we take the mole fraction in solution and we take the pure vapor pressures, and that gives us the partial vapor pressure that's above, right? Because we've mixed them. But now, this is asking us to calculate the mole fraction of chloroform in the vapor. Well, let's think about this. If I take the partial pressure of chloroform is equal to the mole fraction of chloroform times the pure vapor pressure of chloroform, this was in solution. Oops. Right? What if I replace the pure vapor pressure with the total vapor pressure? Right? Because that total vapor pressure is telling me exactly what is above that solution. So I'm still going to take the partial, because that is what is above the solution. Now we're going to calculate the mole fraction that's in the vapor phase. So if I take the partial and I divide it by the total, I should get the mole fraction of the vapor phase. If we look at our numbers, the partial pressure of chloroform was 50.8 torr. The total pressure was 178 torr. So I'm going to say 50.8 divided by 178. Gives me a mole fraction of 0.285. Oh, yes, good call. I just picked the wrong one. I picked the one for chloroform, for carbon tetrachloride, 50.8. So let's, that's for carbon tetrachloride. Just kidding. So now let's do it for chloroform. So it's going to be 127.2 divided by 178. Hopefully, if I took 1 and I subtracted 0.285 from it, I'm going to get whatever this value is. If I don't, we're quitting. Now let's think about this. I'm going to cover this up for a minute, but then I'm going to open it back up. So if we look at these two and just look at the total, the pure vapor pressure, what just happened? Suppose. All right, for those of you online, our screen just turned off. Sorry. Don't know what's happening. So if we look at these two, we see that chloroform has a higher vapor pressure than does carbon tetrachloride. That tells us that it's going to be more volatile, right? It's going to push more up into the vapor phase, which makes sense when we calculate that chloroform has the larger mole fraction in the vapor phase. Does that make sense? You know, you can go back and listen to the video. Sorry. I know it's a lot. I mean, this is literally one chapter in a whole day. All right, now, why is this useful? Who even cares about vapor pressure? Who even cares? Well, if you're going to medical school, you probably, need to think about it when you're talking about capacity of the lungs and what's going on and collapsed lungs. But if you're going into industry, if you've ever ridden down I-26 towards Charleston, and on the right-hand side of the road, it used to be called National Welders. It used to be called, I don't even know. I think it was Airgas. I don't even know what it's called now. But it's got these really tall, skinny buildings. They're not this big. They're obviously bigger. But they look like just very small towers, right? Those are distillation columns. And they are taking air out of the atmosphere and separating it into oxygen and nitrogen and the different components. The way they do that is based on volatility, right? Based on moving that into the vapor phase. But the way they do it is they cool it down, pressurize it, cool it down into a liquid. And then they take that liquid and heat it until the first one raises up into the vapor phase, and they can collect that. And they keep doing that until it's pure. And that's called distillation. You will do it in organic chemistry when you take it. You have to set it all up and all this stuff, and it breaks, and don't worry about it. They'll just give you new pieces. We are done with chapter 12. So, here's my question. Do you want me to keep going into chapter 14? Do you want me to give you a break before recitation? Because recitation starts at 12:20. And it is, break please, it is only 11, right at 11:30. So you're going to have about a 50-minute break. That gives you a little more time to eat and do something. All right, we're going to stop here. We will be back 8:30 in the morning with me. Again, sorry. You're stuck with me. But if you have questions, stay behind. If you don't, take a break. How about that? And you're in this room for recitation, so use this time to do homework. If you're having problems getting into the homework, let me know. The good thing is, when we finish chapter 14, we will have a lot of time to review before the exam. So that's a good thing. And I will hold live reviews too, like at night. Not during the exam, obviously, but. No, we don't. I sent out an email. We're not using iClicker. I mean, I can kind of count how many people are here. I'm good. You know, I'm not. Okay, Mark, you and I need to get together on that. So I'm not a stickler. If you guys wake up one morning and you're like, I don't really want to drive in, and you want to join online, that does not bother me. I'm here because I know some people want it in person, and I know that some people prefer to lay in their bed and sleep and pretend like they're logged in. And that's completely fine, right? Everybody, handles it differently. So, but yeah, you can go back and forth if you want to. Mm-hmm. All right, Mark, I'm not sure. Absolutely, Haley. Yes. Mark, do you have an account set up? Did you go to the? Your homework not working either?
Yeah, I was going to click on, the thing on my phone, it says, how about I go back?
Okay, let me see here. Go back to the.
What word?
Yeah.
Is this the graphics?
Okay.
I don't know if that's happening.
Yeah, okay, so I'm gonna watch this. I'm gonna share so he can see what I'm doing. So, let me make sure it's just- yeah. Okay, so when I click on here, so I click here. When I click here,
Let me try maybe a different browser. Or I guess I go.
I'm in Google Chrome. Let me see if I can fix the link. I don't. I mean, I know it's open. I don't. Can some of y'all log into homework?
I still have to buy it. You have an account. Let's see.
It lets. Yeah.
See, I think it might be a little more easy because I just like searched it.
Somewhere. What? Yeah, sometimes it has to do with allowing it. Let me see what it's called. It is called, I don't know. I'm gonna find it there. Somewhere in security, site settings, pop-ups and redirects, because it is a pop-up.
So it was in security.
Mm-hmm.
Hello.
And then somewhere, see like down here, you have these added, you need to allow it, yeah, you have to add.
Okay, let's see if it works out. Maybe you'll ask me. Okay, let's see. I can up it.
Let me see what Dr. Taylor Perry's doing right now, because she's the expert. Hey, what common errors when somebody's trying to log in using my link in Blackboard to Achieve, it just keeps giving them an error. It doesn't even say what the error, it just says error. It's two people so far, but other people can get in. try Firefox. Gee. Mark, try using Firefox. But other people it's allowing in, I don't understand. Can you check it, see if I have it set up right? I know, it lets me right in. Yeah, it lets me right in. Nope. They tried. I added you. Oh, the sheet, okay.